Chapter 7 has to do with linear momentum. All right. We're talking with momentum concerning collisions. Okay, so when two things collide, what will their momentum be? How can we determine that? We're going to look at two specific types of collisions. Okay, does anyone know the two types of collisions? Off top. Elastic and inelastic are the types of collisions we're going to talk about. Okay, so elastic collisions are where objects rebound off of each other. They would hit and then bounce back. Inelastic collisions would be when they combine and stay as one unit. Momentum is a vector quantity, which means it must have what two things? Magnitude and direction. So magnitude is the size or the number. Direction can be east, west, north, south. It could be a positive or a negative. Okay, remember that with vectors, a negative can indicate a direction. Momentum is a vector quantity because one of these two variables is a vector quantity. Which of these two variables is a vector quantity? Velocity. Good. Velocity. Okay, momentum has to be in the direction of the velocity vector. So overall momentum should be in the direction of the velocity vector. If I'm running to the east, my momentum should therefore be to the east. There's no fancy name for a unit for momentum like newtons or joules. It's just kilograms times meters per second. That means mass must be in kilograms, velocity must be in meters per second. Okay? So when we're dealing with momentum, we have to put our mass in kilograms, have to put our velocity in meters per second. Okay? The usual. Okay, so let's look at an example. If you don't necessarily have to write this down, this is just conceptual. If you have a big truck and a small car that are moving at the same velocity, which has the greater momentum? Big truck. Which would be harder to stop? Big truck, because its mass is bigger. Okay, so although they're moving at the same velocity, the truck's momentum is bigger, which means it's harder to stop. It's going to take more of a force to stop that object. Make sense? Okay. So let's look at the forces it's going to require to make those things come to a stop. Okay. You use forces to not only make things come to a stop, but even make them change direction. Okay, that would change your momentum because momentum is a vector quantity. Okay, so if you change direction, that's also a change in momentum. This is Newton's second law. We know Newton's second law pretty well. Force equals mass times acceleration. What's this Greek letter mean? Sigma, so it's the sum of forces. So basically this just means net force. Okay, net force equals mass times acceleration. I'm going to show you how we can incorporate Newton's second law into momentum. Again, the derivation you don't have to know. It's the final product that you'll be interested in. Okay, so if sum of forces or the net force equals mass times acceleration, we can substitute in acceleration for delta V over delta T, because that's what acceleration is. It's a change in velocity over a certain period of time. From there, we'll take mass times delta V on the top and get delta mv over delta T. And delta mv is momentum. So now we say force equals momentum over time. And it can...
Do you want us to write all of those down into the bottom?
Nope, just the bottom one is the only one you need. Okay, so force equals delta P over delta T. Okay, so change in momentum over a change in time would be equal to our net force. Okay, the sigma here just means sum of forces, the sum of those. We mean that that means just the net force is the sum of all forces. Okay. This equation is sometimes written a little bit differently. Sometimes written like this: F times T equals mass times velocity. Okay, this is equal to momentum. This is the same equation right here. It's just written a little bit differently. You might write that down. We won't use it a lot, but we might every once in a while if we are given those variables. Okay. If you're given these variables, we could just solve for momentum and plug it into this equation, but this way you have it both ways. Sorry. Okay, the example for this is in your book if you want to follow along. If you want to look at the diagram, it's on page 182. But it says water leaves the hose with a rate of 1.5 kilograms per second at a speed of 20 meters per second and is aimed at the side of the car, which stops the water. Okay, so the car is then exerting a force on the water to make it stop. What's the force exerted by the water on the car? Okay, so what's the delta mean by our momentum? Change in or final minus initial. So if we're looking at this water, what's its final momentum? Sorry. All right, here we go. Okay, what's this water's final momentum? 0, because it comes to a stop. Its initial momentum is going to be its mass times its velocity. So this kilogram per second is telling us that for every 1 second that this hose flows, you'll have 1.5 kilograms of water coming out. So we'll just use the time frame here as 1 second. Okay, so in this 1 second time frame, we have 1.5 kilograms of water moving at 20 meters per second. Okay. All that's going to be over our time period, which we chose to be 1 second. Okay, because we know that in 1 second, 1.5 kilograms of mass is involved. Kilograms of water.
What's the 0 for?
Because the final momentum of the water is 0 because it comes to a stop at the car. Okay, so since delta P means final minus initial, that's where we get the 0. Okay, so this force that we get out, what's our number end up being? Negative 30, okay? We're looking at this water coming to a stop, which means that this is the force that the car is exerting on the water to make it stop. Okay, it's exerting a force of negative 30 newtons to make this water stop. Okay, but the actual question is, what is the force exerted by the water on the car? So what would that value be? Positive 30. If this is the 30 newtons of the car on the water, we're trying to find the force of the water on the car. Okay, so Newton's third law says every action has equal and opposite reactions. That means that our actual answer should be positive 30 newtons. In colliding objects, momentum is always conserved. Whether it's an elastic collision or an inelastic collision, momentum is conserved. Okay, it doesn't matter what the mass or the velocity of the objects is. There won't be any huge loss or gain in momentum. It's conserved. Okay, so that means the momentum before the collision is going to equal the momentum after the collision. And here's our equation for that. This is momentum before, this is momentum after. Do you know what this prime means right here?
After it's all changed.
This is basically saying velocity final. Okay, this is called a prime, this little apostrophe right here. So V prime would be its velocity after the collision. Okay, you can think of it as kind of final. So this would be the velocity of our second object after the collision. So the 1 and the 2 tell us which object we're talking about. So this is object 1 before the collision, this is object 2 before the collision, object 1 after the collision, and object 2 after the collision. Okay, so the prime tells us that it's after these two have collided. This is what our momentum should be. Okay, this equation right here is used for elastic collisions. So when things hit and rebound off each other, hit and move back. Okay, let's try one. We want to find the recoil velocity of a 5 kilogram rifle that shoots a .05 kilogram bullet at a speed of 120 meters per second. Okay. So we'll use our M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. Okay, so what's happening is this rifle is sitting at rest. It fires a bullet. The bullet leaves the rifle away from you. The gun will kick back at your shoulder. Okay, so they go in opposite directions. Since it begins at rest, what does that mean both of these terms should be? 0. Okay, since it begins at rest, those are both going to be 0. What do you want the first object to be, the rifle or the bullet? Rifle. Okay, so we're going to plug in our mass and our velocity of the rifle after this has taken place, okay, after this collision. So mass of the rifle is 5 kilograms. Velocity of the rifle is what we're solving for. Okay, so we can't plug that in. Mass of the bullet is 0.05. Velocity of the bullet is 120. So when we solve this, this gives us 6. So now we have 5 V1 prime equals 0. So we'll subtract 6 over to the other side. So negative 6 equals 5 V1 prime. Divide by 5, and that means our velocity of the rifle should be what? Negative 1.2 meters per second. Okay, what's the negative tell us here? Yeah, that's going backwards. Okay, since we chose the rifle or we chose the bullet direction to be positive as it leaves the rifle, this rifle is going the opposite direction, so it's a negative. Okay, so in these vector quantities, a negative can give us an idea of direction. Okay? Make sense? Okay. Let's try an inelastic collision. So inelastic collisions mean two things hit and they stick together and they'll keep moving. Okay, so I have an example here with two trains. Okay, and if you want to look at it, it's on page 184. But here's the first train sitting at rest. Okay, the second train comes in and meets the first train. I know, okay. So it comes in and meets the first train. This one's traveling at a velocity of 24 meters per second before the collision. Okay, so one's at rest, the second one comes in to meet it, bumps it, they collide, they stick together, and they're going to keep moving. So we want to find out the velocity of these two objects moving after the collision. Okay, so after their collision, their masses are now connected and they become one object in our view. Okay, so we want to find the velocity prime of these two objects. Okay, this is the equation that we'll use. Before the collision, they're both separate objects. After the collision, they are one object. So it's m1 plus m2 times v prime. So you'll get the momentum of this now singular object. Okay, so we'll call this one m1. Or this one object 1, this one object 2. Both of these objects, both of these trains have a mass of 10,000 kilograms. Okay, both of them have a mass of 10,000 kilograms. So we'll take 10,000 times 0 plus 10,000 times 24. That's before. Now after the collision, we're going to combine those two masses. So 10,000 plus 10,000 times v prime. Because that's what we want to solve for, is the velocity after those collisions. Okay, I'm going to move my equation down a little bit. So we're going to end up with 240,000 on the left side, 20,000 v prime on the right side. So what do we get for our v prime? 12 meters per second.